Hi everyone, I'm Guan Yang, now I'm a PhD student in National Taiwan University. And today I would like to introduce the application of simplified swarm optimization (SSO) on graph convolution network (GCN). First, we know that enhancing the performance of neural network model is crucial, and there are several methods to achieve this, including data augmentation and model architecture adjustment or hyperparameter optimization. However, collecting data can be challenging and costly, and changing the model structure often leads to increased training time. Therefore, hyperparameter optimization provides an efficient alternative. There are various methods to hyperparameter optimization, such as uh, genetic algorithm or particle swarm optimization. However, these methods can be complex and often changing the model structure or combining different algorithms. These complexities make them difficult for users to understand and implement. Therefore, there's a need for a simpler algorithm that optimizes hyperparameter without changing the model structures. And first, I will talk about our methodology, SSO-GCN. Before introducing simplified swarm optimization, I would like to first introduce our encoding of the solution structure, which is the encoding method of hyperparameter. We encode important structures in GCN and commonly use variable hyperparameters for CNN and define 8 variables. We define common search region for these variables to find hyperparameters that achieve the best accuracy. After understanding our encoding, I want to introduce simplified swarm optimization. Uh, the core of this algorithm is the update rule, update mechanism, and the mechanism is the algorithm first will update each variable xij based on the value of uniform distribution from 0 to 1, and the probabilities CG, specifically if uniform distribution fall with 0 to CG, the variable adopts the global best value, GJ. And if uniform distribution falls within CG to CP, the variable adopts the personal best value. And if uniform distribution falls within CP to CW, the variable remains unchanged. Finally, if uniform distribution falls within CW to 1, the variable is set to a random feasible value x. And this process continues iteratively, allowing the swarm to explore the solution space effectively and converge towards the optimal solution over generations. This is an example of SSO. Consider the example with multiple hyperparameters and their respective value. The SSO algorithm updates their parameter by considering the global best, personal best, p-value, and random value within variable bounds. The new x1 in yellow is an example of new generator solution. This is the flowchart of SSO. Firstly, we start with the initialization phase. At the very beginning, we randomly initialize the positions of all the particles and calculate the objective function value f for each of these initial positions. And after this, we determine the global best position, represented as G by finding the particle with the best objective function value among all the particles. Next, we set the initial values for our counters. We initialize the iteration counter to the t to 1 and the particle index I to 1. Moving on the update phase, we update the position of the current particle x using a specific equation, referred to as equation 2.11 in the flowchart. After updating the position, we calculate the new objective function value, f, and we then proceed to the improvement check. If the new objective function value f is better than the current best, for the particle, we update the particle's best position, p, to the new position, x, and also update the best objective function value, f. Following this, we check for the global best. If the new objective function value, f, is better than the current global best value, f, we update the global best position, g, to the new position, x, and also update the global best objective function value, fg. Next, we increment the counter and the loop through the particles. We increment the particle index I if all particles have been processed, meaning I is greater than or equal to the maximum number of particles max. We reset I and increment the iteration counter t. And we also check if the maximum number of iteration ngen has been reached. If it has, we stop the algorithm. And finally, if the maximum number of iteration hasn't been reached, we go back to updating the position and continue the loop. So in summary, this algorithm continuously updates the position of particles based on their own experience and the global best, iterating through the process until the stopping criteria are met. So the main contribution of our study are as follows. First, the hyperparameter optimization algorithm termed SSO-GCN is proposed to enhance the performance of graph convolution network. And SSO-GCN represents the first algorithm based on SSO specifically designed to improve GCN. And third, the SSO method can be identified the optimal hyperparameters, and last, SSO demonstrates significant potential for enhancing the performance of GCN network architectures. Next is our experiment. First is experiment setting. The experiment setting involves various hyperparameters such as number of convolution layers, optimizer, activation function, number of approach, number of neurons in each convolution layer, dropout rate, learning rate and waiting decades. And for instance, the number of convolution layer is set to 2, and the optimizer can be Eden W, Eden Gray, ENX Gray. And the number of approach is set to number of epoch is set to 200. And the range of number of neuron dropout rate, learning rate, and weight decay is shown as below. And the probability CGCP-CW is set to 0.4, 0.7, and 0.9 respectively. And the number of solutions set to 30, and the number of generations set to 20. In our experiment, Python, PyTorch, and PyTorch geometry is used. And hardware such as CPU, GPU, and RAM is shown as below. And in our experiments, dataset Cora, Sizeer, and PubMed is used. There are various class, clone, age, and features, and the number of training nodes is equal to the number of class multiply 20. They have fixed validation nodes and text nodes, and there are 500 and 1,000 respectively. In our experiment, there are need to follow these 3 steps. First, conduct initial run to identify the optimal activation function and optimizer without any constraint. Second, when the best of optimal activation function or optimizer is found, we need to fix it and try to find the optimal structure or other hyperparameters such as dropout rate and weight decay in following runs. Optionally, you can implement the learning rate scheduler or data augmentation method to find the optimal solution if necessary. In our experiments, we can find the optimal activation function and optimizer. Say for example, hypertension is the best activation function and the best optimizer is integrate. So we fix it in the following experiment. And finally, we find the Cora, Sizeer, and PubMed has a better accuracy within SSO GCN, and it increased around 2%, and it is so significant. Also, the improvement in PubMed is not significant enough. Therefore, I believe that an SSO GCN has potential to increase the accuracy, but we need more experiment to check this potential. Yeah. In conclusion, this result demonstrates the SSO is an effective method to identify optimal solution in GCN. SSO can suggest crucial hyperparameters such as activation function and optimizer, and also it can find the optimal solution for SSO GCN. Additionally, we think that SSO can extend to other neural network architectures, and maybe it is a powerful algorithm for hyperparameter optimization. And we will still explore using it to improve GCN for security-related datasets. And this is a reference. That's all. Thank you.